Good evening, everyone. In the last class, we discussed about the Biot law, and we also applied a Biot law for the calculation of the magnetic field due to finite line of current, right? Finite line of current, right? There was current I flowing through the conductor, right? Which was of finite length, right? So at a distance t, we had to find the magnetic field due to the line current, right? So at a distance of d, we found that it depends upon the angle made by the point, right? With the two ends of the wire, right? Sine of angle made by the point with the two ends of a wire, right? You can see here, this is the point P at a distance of A from this point O, right? And we have two ends A and B, and phi 1 and phi 2 are the two angles which are made by this point P with the ends of this wire A and B, right? So finally, the final result was, it was mu naught I upon 4 pi A, right? Sine of phi 1 plus sine of phi 2, right? This was the final result. So we'll be doing some of the questions related to this, and we'll be further applying the Biot law for the further calculation of different geometries for the calculation of magnetic field, right? So let's discuss this question number 1 here. You can see here we have an infinite line charge, right? So this is an infinite line, right? The current I is flowing through it, right? So it tends to plus infinity and minus infinity, right? And this is the point P here. And we have to find the magnetic field due to this infinite line, right? Magnetic field due to infinite length wire, right? At this point P, right? So we discussed that in the last class. It actually depends upon the two things. One is the distance between from the center of this line, right? Another is the angle made by this point P with the ends of this wire, right? So let's suppose this was the phi 2 angle, right? This angle was the phi 2 angle. This angle was the phi 2 angle, and this angle was called as phi 1 angle, right? This is phi 1 and this is phi 2. This is phi 1 and this is phi 2. That was for finite length of wire, right? But this is an infinite length of wire, right? So when this end of this wire tends to infinity, then you can see that if we rotate this line, this rotate will become at infinity. This line will actually become parallel to this wire, right? Parallel to this wire. And when this line will become the parallel to this wire, then at that time, at infinite distance, this angle here will be a 90-degree angle. And from lower end also, this angle will be equal to 90 degree. Or we can say that for infinite length wire, phi 1 and phi 2 become 90 degree each, right? They become 90 degree each, correct? And the magnetic field at this point will be, given by, that will be mu naught I upon 4 pi d sine of phi 1 plus sine of phi 2, right? This will be the magnitude of the magnetic field at this point, right? And phi 1 and phi 2 is 90 degree each. So it means it will be sine 90 plus sine 90, that will be twice sine 90, that will be 2, right? So magnetic field at point P will be nothing. It will be mu naught I upon 4 pi d, right? Multiplied by this 2, right? So for infinite length wire, the magnetic field at this point will be equal to mu naught I upon 2 pi d, right? This will be the magnetic field at this point P due to this infinite wire, right? So mu naught I upon 2 pi d is the magnetic field at this point. And the direction of this magnetic field, we can find the direction using the right hand thumb rule, right? So if we place the thumb in the direction of this current, right, and then the direction of the palm at this point P will gives us the direction of the magnetic field, right? So this magnetic field here is actually perpendicular to this plane and into the plane. So we'll represent it by a cross symbol, right? Cross symbol, right? So this is the direction of, or we can say that it's in minus k cap direction, right? Minus k cap direction, or we can say that P vector is nothing. It's actually mu naught I upon 2 pi d in the vector form, that will be in a direction minus k cap, right? So this will be the vector form of the magnetic field due to this infinite length of wire, right? Let's discuss this question also. Find magnetic field due to semi-infinite length wire at point P. Now, this is a semi-infinite wire, right? Previously we discussed the infinite wire, but now this is a semi-infinite wire, and this is the point P where we have to find the magnetic field due to this semi-infinite wire, right? So what we have to do is that we will use the same result, right? The result was B was equal to mu naught I upon 4 pi d, mu naught I upon 4 pi d, right? That was the magnetic field, right? Multiplied by this sine of phi 1 plus sine of phi 2, right? Sine of phi 1 plus sine of phi 2, correct? And this phi 1 is the angle made by this point P with the lower end of the wire, and phi 2 is the angle made by this point P with the upper end of this wire, right? So you can see that at one of the ends, the line tends to the infinity, right? So if the line tends to infinity at the upper end of this wire, right, then definitely this phi 2 angle or the theta 2 angle has to be 90 degree, right? So theta 2 or phi 2 will become 90 degree, right? And for this lower end of this wire, right, they're actually at along the same line. So it means that the angle between this point P and this point M is actually 0 degree, right? 0 degree, or we can say that phi 1 is nothing, it's equal to 0 degree. If phi 1 is 0 degree, then the magnetic field B will be equal to mu naught I upon 4 pi d, right? Mu naught I upon 4 pi d, it will be sine of phi 2, right? Sine of phi 2 plus sine of phi 1. Substituting the value of phi 2 and phi 1 equal to 90 degree and 0 degree, so we'll get P is equal to upon mu naught I upon 4 pi d, that's sine 90 and sine 0 plus sine 0. So it will be equal to mu naught I upon 4 pi d. So this is the magnetic field due to semi-infinite wire, right, at this point P. So we have used the same result for the finite length, right? So we actually have calculated the magnetic field due to infinite straight wire, right? Now let's look at this question here, right? You can see there's a question here. In this question, we have represented a current with a dot, right? It means that this is actually infinite line wire, right? Which is actually moving into the plane, right? And which is actually perpendicular to the plane, and the current is out of the plane, right? Current is out of the plane. So it means that I is actually represented here with a circle with a dot at the center. It means it's a infinite length of wire which is perpendicular to this plane and out of this plane, right? So that's the symbol which it represents, right? So it means that 25 ampere of current is flowing through this wire, right? We have to find this magnetic field again at this point P, whose coordinate is given as 3, 4. 3, 4 is the coordinate of this point P, right? So we have to find the magnetic field here. So we know that it's an infinite length of wire, and due to infinite length of wire, we got the result as mu naught I upon 2 pi d, right? Mu naught I upon 2 pi d. Where d is nothing, d is the perpendicular distance between the center of wire, right? Perpendicular distance between center of wire and this point P, and this point P. So this is the significance of d. So d represents actually the perpendicular distance between the center of wire, right, and this point P. Now we can see that the coordinates of this point P are actually 3, 4. If the coordinates are 3, 4, so the distance OP will be actually under root of 3 square plus 4 square, right? Under root of 3 square plus 4 square, that will be equal to root 25, that's equal to 5, right? And this 5 will be the distance D, right? That will be the perpendicular distance, right? Now substituting the value here, D equal to 5, right? We get the value of magnetic field here as mu naught I has the value of 25 amperes, right, upon 2 pi multiplied by 5, right? Correct. So it will be 5 mu naught upon 2 pi, right? 5 mu naught upon 2 pi. So this will be the magnitude of magnetic field at this point P. That's 5 by 2 mu naught upon pi, right? That's the value of the magnitude at this point B, right? Let's look at this question. We have two infinite wires, right? Two infinite wires, and the current through each of the wire is actually equal to 4 ampere and 6 ampere each, right? Current through these wires are actually equal to 4 amperes and 6 amperes each. So current through these wires are actually 4 amperes and 6 amperes each, right? And there is a point P in between these two wires. The point P is at a distance of 1 meter from the wire which has a current 4 ampere, and at a distance of 2 meter from a wire which is a current equal to 6 amperes. And we have to find the magnetic field at this point. So if we find the direction of magnetic field due to this 4 ampere current, right, it will be perpendicular to this plane and into the plane, right? So we'll represent by a cross symbol. And because of this 6 ampere current, the magnetic field will be perpendicular to this plane, but it will be out of the plane, right? So we'll represent it by dot symbol, correct? So it means the two magnetic fields, because of these two wires, are actually in opposite direction, right? So if we represent this direction with this direct dot direction with k cap, right? Then this direction will be a minus k cap direction, right? So it means it will be a subtraction of the two magnetic fields, right? So therefore, net magnetic field B net will be equal to, you can write it as B1 plus B2, right? B1 plus B2. So B1 vector will be equal to mu naught I is given as 4 upon 2 pi d, right? 2 pi d, and the value of d is 1 here, right? 1 here. And the direction is into the plane of the paper will be represented by minus k cap, right? And similarly, B2 vector will be mu naught I is 6 amperes, right, upon 2 pi, and the value of t is given as 2 meters, right? So it will be 3 mu naught upon 2 pi, right? And the direction will be actually plus I cap, right? It will be plus k cap. So therefore, the total or the net magnetic field in this case will be equal to 2 mu naught upon pi minus k cap plus 3 mu naught upon 2 pi k cap, right? So the net magnetic field will be actually equal to minus mu naught upon 2 pi k cap. So this will be the net direction. It means the total net direction of this magnetic field will be actually into the plane of this paper, right? Into the plane of this paper. So that will be the net the direction of the net magnetic field, right? So finally, the direction of this magnetic field is actually into the plane of this paper. So we'll write it as cross symbol here, right? Into the plane of this paper. The position of point from wire B is given here, right? Where net magnetic field is 0 due to following current distribution. We have two current distributions here, and both the current distributions are 6 centimeters apart. And the current through one of the wires, which is perpendicular to the plane of this paper, right? And out of this paper, right? Out of the plane of this paper, that's 5I, and for the wire B, it's 3I, right? And we have to find the point in between these two wires where the net magnetic field will be 0, right? Net magnetic field will be 0. Let's suppose at some distance, at a distance of x, let's suppose at a distance of x from this wire A, the magnetic field will be 0, right? Why the magnetic field will be 0? You can see that if we find the direction of the magnetic field, right? Direction of the magnetic field due to both these wires, right? So at this point P, the direction of the magnetic field will be opposite in direction, right? So they will cancel out each other, right? So let's find out the point where actually the total magnitude of the magnetic field will be equal to 0, right? They will be canceling out each other, right? So if this distance is x, then this distance will be 6 minus x, right? 6 minus x, correct? So the net magnetic field here, B net will be actually equal to P1 plus B2, right? B1 plus B2, right? Correct? Or we can say that the mod of B1 is equal to mod of B2, right? Then the total resultant magnetic field at this point P will be equal to 0, right? The magnetic field due to this wire A at this point will be mu naught I is 5I upon 2 pi T. So the distance is here X and it is mu naught. Current is 3I upon 2 pi T. T is 6 minus X, right? 6 minus X, correct? So mu naught I will get cancelled, right? 2 pi and 2 pi will get cancelled. So we'll be left with here 5 is equal to 3 upon 6 minus X only, right? Or you can say that it will be 30 minus 5x, that will be equal to 3, right? That will be equal to 3, correct? That will be equal to 3. Or from here, 5x will be equal to 30 minus 3, that will be equal to 27, right? And the value of x will be equal to 27 upon 5. So this is the position at which this is the distance from this wire A, or the position from this wire A at which the net magnetic field due to these distributions of current 5I and 3I is actually equal to 0, right? We have already discussed that whenever we represent a current with dot symbol at the center, right? Dot symbol at the center, it means that the current is perpendicular to the plane of paper and away from it. I mean to say that out of the plane of the paper, right? And similarly, if we represent a magnetic field, current by this cross symbol, it means the current is perpendicular to the plane of paper, or we can say into the plane of paper and perpendicular to it, right? So that's it for this question, right? Let's move on to the next concept here. Now, the very important concept, another application of magnetic field is, or the Biot-Savart law is, magnetic field at the center of circular loop or of at the center of any circular arc, right? So we can find the magnetic field due to any circular arc or due to complete circle, right? Due to any loop, right? So whenever we have a loop, right? Whenever we have a loop, then the and the current I is flowing through the loop, right? Then the direction of the current is actually once again given by the right hand, right? What we do is that in case of loop, we curl our fingers along the direction of the current, right? We curl our fingers along the direction of the current. Then the direction of the thumb actually gives us the direction of the magnetic field, right? So you can see here in this picture. So this is the current I. This is how the current I is flowing, right? This is how the current I is flowing, right? Now we are curling the fingers of our right hand along the direction of this current, right? Now the direction of this thumb is giving us the direction of magnetic field, right? It means the direction of the magnetic field will be perpendicular to this plane at the center and out of it. So it will be a dot here, right? It will be a dot here. Similarly here, in this case, it will be a cross here, right? It will be a cross here. So this is how the direction of magnetic field is found, or how the direction of magnetic field is seen with the help of this right hand rule, right? Now let's try to calculate, or let's try to find the magnetic field, right? Magnetic field due to circular ring, right? This is a ring or arc, you can say, or loop, correct? So we have to find the magnetic field due to this circular loop at the center, right? Magnetic field due to this circular loop at the center, right? Of radius r, right? You can see that the current through the loop is actually the current flowing through the loop is I. Current flowing through the loop is I, right? And radius of this loop is r, right? So we will again use Biot-Savart law, right? We will again use Biot-Savart law. Using Biot-Savart law, right? So Biot-Savart law is nothing. It gives us the magnetic field due to element of current, that's mu naught I TL sine of theta upon 4 pi r square, right? So this is the magnetic field given by the Biot law, right? You can see in this picture, we have a circular loop of radius r and current I is flowing through it. We have chosen a current element. This is the current element, right? This is the current element here. This is the current element of length dl. So this will be a dl vector, right? And this dl vector will be actually tangential, right? It will be tangential at this point. It means the direction of this dl vector will be tangent to this circular loop, right? Tangent to this circular loop. And one more important point is that this is the point C where we have to find the magnetic field due to this complete loop, right? So if we connect this point C with this current element, right, and you can clearly see that the angle between this current element, right, it's a tangent, right, and this C distance from C to the surface of the circumference of the circle, right, that's the radius. You can say that radius and the current element are actually perpendicular to each other. Why they are perpendicular? We know in a circle, radius is always perpendicular to the tangent, right? Really, radius is always perpendicular to the tangent. Now here in this case, TL vector is the tangent vector, right? Is the tangent here, right? It's actually moving tangentially, right? The direction of this TL vector is actually tangent at this point, right? So radius and the tangent are always perpendicular to the circle, right? Perpendicular in case of circle, right? So this angle theta here is actually a 90-degree angle. So we can say that this sine of 90-degree will be here equal to 1, right? So our sine theta is nothing. It's actually sine of 90 here. That is equal to 1, right? That's equal to 1, correct? So our magnetic field dB here will be, it will be mu naught I upon 4 pi. Now this is a small r square, and the distance between this current element and this center C is the radius of the circle. So we can replace it by capital R square, right? And which is a constant for this case, right? So mu naught I upon 4 pi r square, right? Into dl, right? Because sine theta is sine 90 is equal to 1, right? Now we have to integrate it on both sides to calculate the total magnetic field because of this complete loop, right? Total magnetic field because of this complete loop, right? So it will be actually equal to B, right? Integral of dB will be B. So now you can see that it will be integral of mu naught I, right? Integral of mu naught I upon 4 pi r square is a constant. We'll just take it outside this integral, right? That will be mu naught I upon 4 pi r square. Now integrating this dl element, right? Dl vector, right? You can see that the net integration of this dl length actually gives us the total length of this circle, right? It will give us the total length of the circle, right? And we know that total length of this circle is nothing, it's the circumference of a circle, right? It's the circumference of a circle, and we know that circumference of a circle is nothing, it's equal to 2 pi r, right? Let's replace this TL with 2 pi r here, right? So we can say that mu naught I upon 4 pi r square multiplied by 2r multiplied by 2 pi r. So r and r will get cancelled, pi and pi will go, so we'll be left with magnetic field at the center of a circular loop is mu naught I upon 2r, right? Mu naught I upon 2r, correct? So this is the magnetic field at the center of a circular loop. So it only depends upon two things, right? It depends upon the radius and it depends upon the current I as well, right? So this is the magnetic field due to the circular loop at the center of this circle, right? Let's try to solve some questions, few questions with respect to this circular loop. You can see we have a question here. Circular loop is made by a wire of length 7.5 meter. If current 5 ampere is flowing in the loop, then magnetic field at the center is, right? So it means that we have this circular loop here. We can just draw this circular loop, and the length of this circular loop is 7.5 meters. It means that the total length is actually 7.5 meters, right? So we can say that this is the circumference of the circle, that's 2 pi r, that's given as 15 upon 2, right? 15 upon 2, that's the 7.5 meters, right? And the current through the circular loop is actually given as equal to 5 amperes, right? That's actually given as 5 amperes, or we can say that the radius of the circular loop is nothing, it's 15 upon 4 pi, right? 4 pi. That's the radius of the circle. Therefore, the magnetic field at the center of the circle will be mu naught I upon 2r, right? Mu naught I upon 2r, that will be mu naught multiplied by this I is 5, right? And 2 times r, 2 times r is nothing, it's 15 upon pi, right? It's 15 uh, upon 2 pi, right? 15 upon 2 pi, right? So it will be 15 upon 2 pi here, right? So it will be equal to, final answer will be equal to 2 pi mu naught upon 3. So this will be the final magnetic field at the center of this loop, right? So at the center of a loop of this wire, right? The magnetic field is actually 2 pi mu naught upon 3, right? This will be the total magnetic field at the center of this loop, right? Now let's move on to the another similar question here, right? Now this time the question consists of two concentric circles, right? The question actually consists of two concentric circular coils of radius 5 centimeter and 10 centimeter each, and they are placed in same plane, right? They are placed in same plane. If current 0.2 ampere is flowing in both coils in same direction, then find magnetic field in the center, right? Now you can see we have two coils here, right? This is the coil number one, right? This is the coil number one, correct? And the current flowing is 0.2 amperes, right? Each. And in this coil also the current flowing is 0.2 amperes, correct? So radius of the inner circle is 5 centimeter and the radius of the outer circle is 10 centimeters, right? We have to find the net magnetic field. The total magnetic field will be net magnetic field will be actually, you can see the direction of the magnetic field at the center of this at the center of this concentric circle will be actually out of the plane of this paper, right? Out of the plane of this paper, right? So the total magnetic field will be actually P1 plus P2. So this is the net magnetic field at the center of these two circular loops, right? Now let's first try to calculate P1, that's the magnetic field due to inner loop, and then we'll calculate the P2 magnetic field due to outer loop, and then we'll add both the magnetic fields to get the total magnetic field at this center, at the common center of these two circular loops, right? So B1 will be equal to mu naught I, that's 0.2 each upon R, 2R, right? 2R. And R1 is given as 5 centimeter, right? We'll just take it into meters. We'll divide it by 100, right? And B2 will be equal to 0.2 mu naught upon, it is actually 2 times 10 centimeters the radius, so 10 upon 100, right? So it will be 1 upon 20, right? It will be 1 upon 10, right? So B1 will be actually equal to 4 times mu naught, right? 4 times mu naught upon 2, right? That will be equal to 2 times mu naught. And B2 will be actually equal to 2 mu naught upon 2. That will be equal to mu naught, right? So it means the total magnetic field B net at the center of this loop will be actually equal to 3 times mu naught. So this will be the total magnetic field at the center of these two concentric circles or two concentric loops, right? Now this is another two symmetrical current carrying rings, right? You can see that we have two symmetrical current carrying rings or loops, you can say, are placed perpendicular to each other. So this is the fashion in which they are placed, right? With their common center, right? If magnetic field at the center due to one coil is B, then find net magnetic field, right? So due to both of these circular loops, right, the magnetic field is B individually, right? Because they are carrying the same current, right? Two symmetrical current. So it's saying that in this question there are two symmetrical current carrying rings. It means the current through each of this ring is actually same. That's equal to I here, and that's equal to I here also, right? And then let's suppose B is the magnetic field at their common center, right? At their common center, this is the magnetic field B. and the radius of each coil is actually equal to r, right? Now let's try to find the direction due to each of these coils, right? Direction of magnetic field due to each of these coils. So if we find the direction of magnetic field due to this coil 1, you can see that if we curl the fingers of a right hand along the direction of the current, then thumb points out in the direction of this plus axis, right? Or we can say due to this first loop, the direction of the current direction of the magnetic field is along plus I cap, right? It's along plus I cap. And similarly, the direction of magnetic field due to this second loop, right? Due to this second loop is actually along y direction, and here due to upper loop it's along x direction, so we can write it as j cap, right? It means that the B net magnetic field is nothing, it's actually equal to bi cap plus pj cap, right? So the magnitude of the total magnetic field is nothing, that's the modulus of this, right? That will be equal to under root of t square plus b square, that's equal to 2b square, or we can write it as b root 2. So b root 2 is the final answer for this question. So net magnetic field here is b root 2, or we can say that net direction of this magnetic field will be actually along this direction. So this will be the direction of the net magnetic field at the center, right? This will be the direction of the net magnetic field at the center, right? Now let's try to find the magnetic field due to this arc, right? Initially, we were trying to find we found the electric field, or sorry, magnetic field due to complete circular loop. But in this question, we'll try to find the magnetic field at this point too, due to this arc, which is actually making an angle of alpha here, right? An angle of alpha here, right? So we have to find the magnetic field, right? We'll once again use the Biot-Savart law here, right? Biot-Savart law. Using Biot-Savart law here, right? Right? This is the Biot-Savart law here, right? Now, let's suppose this is the length element here, right? And we know that this length element is actually perpendicular to this radius, right? Because it's tangential, right? So tangent is always perpendicular to the radius of a circle, right? So we can easily say that in this case also, this angle has to be equal to 90 degree, right? 90 degree. So using Biot-Savart law again, our B will be nothing. It will be equal to mu naught I upon uh, mu naught I upon 4 pi r square, right? TL sin theta, right? TL sin theta. This will be the Biot-Savart law, right? Mu naught I TL sin theta upon 4 pi r square, right? Now, once again, this sine of theta is nothing, it's sine of 90 degree. That will be equal to 1, right? That will be equal to 1. So we can replace this sine 90 with 1. That will be left with mu naught I dl, right, upon 4 pi capital R square, right? Capital R square. Let's suppose this is the element of length dl, right? Length dl. And now this length dl actually, let's suppose this length dl here subtends an angle of d theta here, right? It subtends an angle of d theta here. So it subtends an angle of d theta here, right? So it subtends an angle of d theta here, right? So this angle d theta will be nothing, right? It will be dl by r. That's the radius of the circle, right? So if d theta is the angle subtended by this dl element at the center, then this d theta has to be equal to dl upon r, right? So this is the angle, that's the length of the arc upon the radius, right? So dl upon r. So it means that we can write dl as rd theta, right? Rd theta, correct? Rd theta. So rewriting it as rd theta, so our P magnetic field will be equal to mu naught I upon 4 pi r square, right? Mu naught I upon 4 pi r square. So dl is replaced with, it's the dp magnetic field. It's a very small magnetic field due to this length element, right? So multiplied by this dl, replacing this dl with rd theta, right? Now integrating on both sides to calculate the total magnetic field here, right? So this r and r will get cancelled. We'll be left with mu naught I upon 4 pi r, right? And the integral of this d theta, right? And we have to integrate with respect to this angle subtended by this length element, right? So we're going to integrate it from completely from 0 to the total angle that's actually equal to alpha, right? So we'll integrate it from 0 to alpha, right? 0 to alpha. So the total magnetic field B here will be actually equal to integral of d theta will be theta, and the upper limit is alpha. So we can write here is mu naught I times alpha upon 4 pi r. So this will be the total magnetic field due to this circular arc at the center of this circular arc, right? So mu naught I alpha, right, upon 4 pi r. So this is the magnetic field at the center of this arc. So we can also recheck it. Let's suppose for the complete circle, this alpha will be actually equal to 2 pi, right? Alpha will be equal to 2 pi. So it means that we can just write here B is equal to mu naught I times 2 pi upon 4 pi r, right? 4 pi r. This pi and pi will get cancelled. We'll be left with mu naught I upon 2r. Mu naught I upon 2r. That's the magnetic field due to the complete circle at its center, right? That's the magnetic field due to the complete circle at its center. So this is the magnetic field we calculate due to a circular arc, right? Due to a circular arc. And similarly, we can have different cases, right? Let's suppose if we have a case like this, we have a semicircle here, right? Semicircle here, right? And the current I is flowing through it, right? Now this semicircle will subtend an angle of pi or 180 degree at the center, right? Pi or 180 degree at the center. It means that the magnetic field because of this semicircle at this center will be actually equal to it's going to be equal to B is equal to mu naught I alpha, right? Mu naught I alpha. So alpha is actually pi here upon 4 pi r, right? 4 pi r. So pi and pi will get cancelled. So the magnetic field due to this semicircular arc will be actually mu naught I upon 4r, right? Mu naught I upon 4r, right? Similarly, if we have this quarter circle, right? This is a quarter circle. Let's suppose this is a quarter circle, right? This is a quarter circle of length of radius r, right? Now it will subtend an angle of 90 degree at the center, right? This quarter circle. That means magnetic field due to this quarter circle at the center will be nothing. It will be B is equal to mu naught I times alpha. Alpha will be pi by 2 for this quarter circle, right? Upon 4 pi r, right? Now once again this will get cancelled. We'll be left with mu naught I upon 8r, right? Mu naught I upon 8r. So this will be the magnetic field to the center of this quarter circle, right? Magnetic field due to the center, due to this current at the center of this quarter circle, right? Now let's try to solve a few questions here, right? The question you can see here, we have this semicircular arc and this circular arc here, right? They're connected in this fashion, right? So we have to find the magnetic field, right? We have to find the magnetic field due to this system, right? So the total magnetic field here in this case, total magnetic field here in this case will be actually equal to that total magnetic field due to this arc, right? Arc 1 and the magnetic field due to this arc 2, right? This will be the total magnetic field at the centers of these two arcs, right? You can see that this arc is actually a quarter circle, right? It's a quarter circle. It's actually a quarter circle, right? It will subtend an angle of 90 degree here, right? It subtends an angle of 90 degree, right? It subtends an angle of 90 degree here. Or we can say this angle is nothing, this is pi by 2, right? And due to this quarter circle, the magnetic field we actually calculated is mu naught I upon 8r, right? Mu naught I upon 8r. Now this is the 3/4 of a circle, right? It's a 3/4 of a circle, and it will subtend an angle of 3 pi by 2, right? This angle subtended here will be actually 3 pi by 2 at the center, right? So its magnetic field will be mu naught I times alpha. Alpha here will be 3 pi by 2, right? Upon 4 pi r, right? Upon 4 pi r, right? So this pi and pi will get cancelled. We'll be left with 3 upon 8, right? Mu naught I upon r, right? So 3 upon 8 mu naught I upon R, right? So the net magnetic field at the center O, at the common center O, will be actually, you can see the direction, right? You can see the direction of this circular arc here. The direction of this, due to this circular arc, will be actually into the plane here, right? That will be a cross. And direction due to this circular arc will also be into the plane, that will be a cross, right? It means that the net magnetic field at this point will be the factor addition of the two magnetic fields, right? So it means that the net magnetic field B net will be actually equal to 3 mu naught I upon, you can see here, for this circle the radius will be, let's suppose, R1 for this circle, right? Radius is R2, right? We'll just denote the radius as mu naught, as R1 and R2, and which is given here as, for the larger circle, mu naught I upon, that's given as B, right? Mu naught I upon 8B, right? 8B. And for this R2 is actually A, correct? So 3 mu naught upon 8A plus mu naught I upon 8B, right? The net magnetic field here will be actually mu naught I upon, right? Mu naught I. So it will be 3 mu naught plus mu naught, right? It will be 8 will be a common, right? We can just take 8 here also common, right? So it will be 3 by 8, 3 by A plus 1 by B, right? So this will be the net magnetic field at this point, right? So this will be the net magnetic field at this point, at the center of the circle, right? That's the net magnetic field, right? Now let's look at this question. This will be the last question for this session, right? A long wire bent as shown in the figure carries current I, right? We have a long wire which is bent in the as shown in the figure, right? Carries current I, right? If the radius of the semicircular portion is A, right, then find the magnitude of the magnetic induction at the center. So it means we have to find the magnetic field, net magnetic field at the center of the circle, right? So the net magnetic field here will be actually, the net magnetic field here actually will be the magnetic field due to this circular arc, right? Due to this circular arc, and the magnetic field due to these two wires, right? These two wires, right? If we find the magnetic field due to wire at this point, right, it's actually a semi-infinite wire, right? It's a semi-infinite wire. So at this point, the magnetic field, direction of the magnetic field due to these semi-infinite wires will be actually, for this wire, it will be actually in the downward direction, right? In the downward direction like this. So we can say that it will be a minus k cap direction, right? And because of this wire, it will be a plus k cap direction, right? Plus k cap direction, correct? So it means that the net magnetic fields because of these two wires will be actually zero, right? So this magnetic field due to this wire will be cancelled out by the magnetic field due to this wire, because they are at the same distance, right? They are placed at the same distance from this center of the circle. So magnetic field due to this wire and due to this wire are actually in opposite direction and with the same magnitude, so they will cancel out each other. It means that we'll be left out with the magnetic field because of this circular portion only, right? We'll be left out with magnetic field because of this circular portion only, right? And the magnetic field due to this semicircular portion at this point will be actually along minus I cap, right? It will be along minus I cap. So the net magnetic field will be actually, and because of this semicircular arc, we know the magnetic field is mu naught I upon 4r, right? Mu naught I upon 4r, and in the direction of minus I cap. In the direction of minus I cap. So this will be the net magnetic field due to this system of currents, right? So that's it with respect to the calculation of the magnetic fields, right? In the next lecture, we'll be discussing the force due to the magnetic field, force between the two uh, magnetic current carrying wires having some magnetic field, right? We'll be calculating the force between those wires, right? That will be discussed in the next lecture, right? Tomorrow. Okay, let's stop here. Let's meet tomorrow. Till then, take care and goodbye.